Welcome to Secrets of Earth. I'm Patrick Viersba, your guide into the world's most remote corners. Today, we descend further than we have ever gone, past every familiar zone of the ocean, into a place where the Earth itself is alive beneath our feet. Today, we enter the world of the Yeti Crab. Imagine leaving the surface behind. You descend through the sunlit lair where the whales sing. You pass through the twilight zone where the light thins to a cold, bruised purple, and then, almost gently, gives up entirely. You enter the midnight zone, the bathypelagic, where the pressure exceeds 200 atmospheres, where the temperature sits just above freezing, and where the darkness is as complete and as permanent as the inside of a closed fist. For a long time, we thought the deep ocean floor was a wasteland. We assumed that without the sun to drive photosynthesis, without the energy that life on the surface takes for granted, the abyssal seafloor must be essentially empty, a graveyard of cold mud and silence. This assumption held for most of human history, and it was logical. It was also wrong. In 1977, scientists exploring the ocean floor near the Galapagos Rift made a discovery that changed biology permanently. On the seafloor, at nearly 2,500 meters in depth, they found something that shouldn't have existed. A thriving ecosystem. Tube worms, clams, shrimp, bacteria, gathered around cracks in the Earth's crust where superheated, mineral-laden water was venting up from the mantle. Life, abundant and complex, powered not by the sun, but by the chemistry of the Earth itself. In the decades that followed, as submersibles explored more of the deep sea floor, the inventory of vent life grew. And then, in March 2005, a team organized by the Monterey Bay Aquarium Research Institute, operating the research submersible Alvin along the Pacific-Antarctic Ridge, 1,500 kilometers south of Easter Island, found something new even by vent standards. Crawling across the volcanic rock near a hydrothermal vent at a depth of 2,200 meters was a pale, ghostly crustacean, unlike anything in the scientific record. It was roughly 6 inches long, white as chalk, and its claws, long and slender, were covered in flowing, silk-like filaments that billowed as it moved. The team collected a specimen, brought it to the surface, and sent it to the taxonomists. The analysis revealed not only a new species, but a new biological family, a lineage with no close living relatives. They named it Kiwa hirsuta. In Latin, hirsuta means hairy. Kiwa is the name of the Polynesian deity, guardian of the sea. But the world quickly gave it another name, the Yeti Crab, after the legendary creature of the Himalayas whose shaggy appearance it eerily recalls. The Yeti Crab doesn't just survive in one of the most extreme environments on Earth. It has turned that environment into a working farm. And what it grows, and how it grows it, may contain the most important biological implications of anything we will discuss in this series. To understand the Yeti Crab, you have to understand its address. Hydrothermal vents form where tectonic plates pull apart at mid-ocean ridges, opening fractures in the seafloor through which cold ocean water percolates down into the hot rock beneath. The water is heated to extreme temperatures by the geological activity below. Black smokers, the most intense type of vent, can expel fluid at over 400 degrees Celsius, hot enough to melt certain metals. Under the enormous pressure at these depths, the water doesn't boil. It remains liquid, but barely. When it encounters the near-freezing seawater of the deep, it precipitates its mineral load, iron sulfide, copper, zinc, in towering chimney structures that can rise 6 stories from the seafloor, billowing with what looks like black smoke. The fluid is a toxic cocktail of hydrogen sulfide, methane, and heavy metals. To almost any life form accustomed to the surface world, this is instant death. But to the creatures that have evolved to exploit it, it is everything. Because there is no sunlight at 2,200 meters, there is no photosynthesis. There are no plants, no algae performing the conversion of light into sugar that underpins almost all life on the surface of the Earth. Instead, life here is powered by a different equation entirely: chemosynthesis. Certain bacteria, specifically the types classified as epsilon and gamma protobacteria, have evolved enzymes that allow them to harvest energy not from sunlight, but from the oxidation of chemicals: hydrogen sulfide, methane, the toxic outflow of the Earth's interior. They can take these deadly compounds and, through a chain of chemical reactions, produce organic matter, the molecular building blocks that other organisms can eat and live on. They are the base of a food web that exists in complete independence from the sun. This was, when first discovered, one of the most philosophically disorienting findings in modern biology. The assumption that all life on Earth is ultimately sun-fed. Even animals in the deep that eat marine snow, the organic debris sifting down from the productive surface, dissolved the moment scientists saw tube worms the length of a person thriving in absolute darkness, powered by geology. But the Yeti crab is not simply a passive beneficiary of this chemistry. It has developed a relationship with the chemosynthetic bacteria that is unlike anything seen at the vent before. It grows them, tends them, and harvests them from its own body. The Yeti crab lives on a knife's edge between 2 hostile environments. A few inches too close to the vent opening, and the superheated fluid will kill it in seconds. A few inches too far, and it will freeze in the near-zero ambient temperature of the surrounding abyss. Its entire life is spent in a narrow thermal corridor, a Goldilocks zone, measured not in millions of kilometers as we describe planetary habitability, but in centimeters, fractions of body lengths, the width of a single extended claw. Its body reflects this world perfectly. It is ghostly white. There is no evolutionary pressure to produce a pigment in a place where no light ever falls, and pigment is metabolically expensive. Its eyes have degenerated almost entirely, reduced to vestigial structures beneath a layer of tissue. It perceives its world not by sight, but by the chemical and thermal signatures of the water moving around it, the gradient between life-giving vent fluid and lethal cold. And covering its claws, its arms, and much of its body, those extraordinary filaments, dense, silky, pale as frost. They make it look like the artifact of a dream. They are a farm. Under a highly powered microscope, the filaments of a Yeti crab are not an abstract curiosity. They are a densely populated agricultural landscape. Each filament, each seta, is colonized by billions of chemosynthetic bacteria, packed along its surface in thick, matted layers. These bacteria thrive on the hydrogen sulfide and methane emanating from the vent. They are the same class of organism that forms the base of the entire vent food chain, but they are not free-floating in the water. They are growing on the crab's own body, cultivated as a living crop. This is what biologists call an episymbiosis, a symbiotic relationship occurring on the surface of the host rather than inside it. The bacteria get a stable substrate to grow on and reliable exposure to the chemicals they need. The crab gets a source of food it can access at any moment without hunting, without competing, without ever leaving the one narrow zone of the deep sea it can survive in. But the relationship doesn't stop at providing a growing surface. The crab actively manages its crop. Here is where one of the strangest behaviors in the animal kingdom comes in. The behavior that led scientists to title their 2011 research paper, in a moment of rare scientific poetry, "Dancing for Food in the Deep Sea." Scientists observing Yeti crabs through deep-sea camera systems noticed that the crabs don't simply sit still. In a place where stillness would seem like the most energy-efficient strategy, these animals rhythmically wave their claws back and forth through the flow of the vent fluid, slowly, deliberately, again and again, for hours. At first glance, it looks like a behavioral ritual, a form of communication, perhaps a defensive display. But when researchers analyzed it, they found something more precise. The waving is a farming technique. The bacteria on the crab's setae are limited in their growth rate by two factors: the availability of the chemical compounds they need from the vent, and the availability of oxygen from the surrounding seawater. These two resources come from opposite directions: the vent fluid from below, the oxygenated seawater from above. When the crab is still, the bacteria immediately around each seta are limited by what is called a boundary layer, a thin shell of depleted fluid that clings to each filament, reducing access to fresh nutrients. By waving its arms, the crab strips away these boundary layers. It floods the bacteria with fresh vent fluid on one stroke, oxygenated seawater on the next. It is actively ventilating its crop, maximizing the productivity of its bacterial garden through the physics of fluid dynamics. The more precisely it waves at the right speed, at the right angle to the current, the faster the bacteria grow. The faster they grow, the more food the crab has. It has turned its own body into a garden, and it tends that garden with the deliberate, patient motion of a farmer who has learned, through millions of years of selection, exactly what the crop needs. When the bacterial mat is thick enough, the crab harvests it. Along its third maxilliped, a mouth appendage positioned near its feeding parts, are rows of highly modified setae that function as tiny combs. The crab draws its claws through these combs, stripping the bacterial mats from the filaments and feeding the biomass directly into its mouth. The arm is cleaned, the bacteria begin to regrow. The cycle continues. It is a closed loop of extraordinary efficiency. The crab provides the land, its own body. The crab provides the labor, the dance. The bacteria provide the food. And all of it is powered not by the sun, not by anything falling from the surface, but by the internal heat and chemistry of the planet beneath the crab's feet. Consider the implications of this. Colonies of Yeti crabs have been found packed at densities of up to 700 individuals per square meter around vent sites. 700 individuals per square meter, in a place where the prevailing assumption was biological emptiness. These animals are thriving at urban densities, all of them farming their own food from the geological exhaust of the earth. For a long time in biology, the phrase habitable zone meant a very specific thing. It meant the strip of space around a star where liquid water could exist on a planet's surface, close enough to stay warm, far enough away to stay cool. Life, by this definition, was a surface phenomenon. It required sunlight. The deep interior of a world was, by default, sterile. The hydrothermal vent discoveries of the past half-century have systematically dismantled this assumption. But the Yeti crab pushes the argument further than any tube worm or blind shrimp. Because the Yeti crab is not merely surviving in the dark. It has built an economy in the dark. It has evolved a complete, self-sustaining food production system independent of any solar input, powered by chemistry, maintained by behavior, and capable of supporting a population of hundreds per square meter in what was previously considered a void. This matters far beyond the ocean floor of our own planet. Hydrothermal vents, scientists now believe with significant confidence, exist beneath the ice of Europa, one of Jupiter's moons, where a deep liquid ocean is kept from freezing by tidal heating from Jupiter's gravitational pull. They almost certainly exist under the ice of Enceladus, one of Saturn's moons, where the Cassini spacecraft detected plumes of water vapor containing silica particles of exactly the size and type that only form in hot, mineral-rich water. In both cases, the conditions at the seafloor of these ice-covered oceans are thought to closely resemble the conditions around Earth's hydrothermal vents. If life can exist at Earth's vents, not just microbes, but complex multicellular organisms farming their own food in total darkness, then the question of life on those moons becomes genuinely urgent. It is no longer a question of whether the conditions exist. The Yeti crab is the proof of concept. It is a living demonstration that complex life can emerge, sustain itself, and build sophisticated behaviors in the complete absence of sunlight, powered by nothing more than the chemistry of a geological process. The Yeti crab is not simply a weird deep-sea crustacean. It is one of the most important arguments in the search for life elsewhere in the universe. We often think of the abyss as infinitely remote, a realm so removed from our daily lives that it operates in permanent safety behind the barrier of depth. But the Yeti crab's neighborhood is not as safe as its distance suggests. The same hydrothermal vents that support the crab's bacterial garden are also the sites of what geologists call seafloor massive sulfides, concentrated deposits of copper, zinc, gold, and silver, precipitated by vent fluid over thousands of years. In a world increasingly hungry for the raw materials to manufacture electric vehicles, smartphones, and the physical infrastructure of the green energy transition, These deposits have drawn the attention of the deep-sea mining industry. The danger for Yeti crabs is not abstract. Unlike most ocean animals, these crabs cannot simply relocate. They are not visitors to the vent. They are products of it. Their entire biology, the chemistry of their bacteria, the thermal tolerance of their bodies, their behavioral repertoire, is built around one specific type of environment. Destroy the vent, and you do not merely displace the population. You eliminate the only conditions under which that population can exist. A single mining operation, conducted without adequate understanding of what it destroys, could erase an entire Yeti crab population in an afternoon. A population that may have been building itself generation by generation for thousands of years. At these depths, far from any monitoring, the evidence would sink quietly into the sediment. The Yeti crab asks a question that we are increasingly unable to avoid. How do we weigh the value of a discovery against the value of the material it happens to be sitting on? How do we decide when the thing we are weighing is a biological proof of concept for life on other worlds not yet fully understood, existing in a place where we have only just learned to visit? We do not yet have a good answer, but the question is becoming urgent. We share this planet with millions of stories, most of them unfolding in the silence of the deep or the shadows of the canopy. The Yeti crab teaches us that life doesn't simply tolerate the darkness, it builds farms on it, it dances in it. It has been there in the volcanic veins of this planet long before we knew how to look. Thank you for journeying with me into the world of the Yeti crab. I'm Patrick Viersba. There are many secrets of Earth, if you only know where to listen. I'll see you on the next horizon. Until then, follow our coordinates by subscribing to or following the show. It ensures that you never miss a step into the unknown.